Hello everyone and welcome to this lecture. Today we are going to see some examples of coupled differential equation or system of linear differential equation with constant coefficients where we will get repeated eigenvalues. So let us start with an example. Example 1, and we have the system as the following: x1 prime is equals to minus 2 x1 minus 2x2 plus 2x3. Then we will have x2 prime equals to minus 4x1 plus 2x3. Then you will have x3 prime as minus 8x1 minus 4x2 plus 6x3. This is a coupled differential equation for these three variables, and if you write this thing in the matrix form, you will see that the coefficient matrix will turn out to be nothing but minus 2, minus 2, 2, minus 4, 0, 2, minus 8, minus 4, 6. And if you recall, the matrix form had this thing like this, that is x prime equals to x, and we already know from our previous lectures that how to solve this thing. We saw the 2 cross 2 example, so we'll try to follow that and let's see what happens. So first thing first is that we need to determine the eigenvalues, and if you denote the eigenvalues by r, you need to do this A minus Ri, and here I is a 3 cross 3 identity matrix. You need to set this to be 0, and if you do that for this matrix over here, you will find that this will turn out to be r into r minus 2 whole square equals to 0. So this means either r equals to 0 and or r equals to 2. However, r equals to 2 has a multiplicity of 2. This means it's repeated 2 times because there is a power of 2. And now let's learn a new terminology, and this multiplicity, that is the multiplicity that indicates how many times the root have been repeated, it's called the algebraic multiplicity. And there is also a thing called a geometric multiplicity. That means that how many eigenvectors are associated with the eigenvalue. In general, it's 1. That is, if your eigenvalues are distinct, then each of the eigenvalues associate an eigenvector. But here you can see that 0 has a multiplicity of 1. That means it's not been repeated, so it has an algebraic multiplicity of 1, and associated with 0 will be one eigenvector, and that means the geometric multiplicity is also 1. However, since r equals to 2 has been repeated 2 times, we expect that there will be 2 eigenvectors associated with it. So let me just summarize this up. We call a term called geometric multiplicity as the number of eigenvector. Obviously this is not a very formal definition, but it's more of a physical definition. That means since this is a vector, the eigenvector, they also span the space inside which this matrix is defined. That is the vector space itself. So that's why we're calling it a geometric, because it has something to do with the space. So again, as I was saying, the number of eigenvectors associated with each eigenvalue. And this whole multiplicity business is something really deep, but we will merely scratch the surface in our lectures. So let's keep these two basic definitions over inside our head and let's try to do the math. So if you compute the eigenvalue, you can see that there is eigenvalue of r equals to 0. So now we want to calculate the eigenvector, and this eigenvector, let's call this v1, and this is associated with r equals to 0. And if you calculate it, it will turn out to be v1 equals to 1, 1, 2, and you will see there is no ambiguity there. However, when you want to calculate the eigenvector, let's call this v tilde, by which we mean the eigenvector associated with r equals to 2, you will see something a bit weird, and let's try to see what happens. Already you know this from linear algebra, but still let's try to see that. So this was our matrix, and we want to calculate the eigenvector for the eigenvalue 2. So we have to do this -2, -2, then there is a -2 over here, 2 over here, 4, -2, 2, -8, -4, 6, -2, and there is this x1, x2, x3, and this is just equals to this. Now if you calculate this out, you will see that all these 3 rows will eventually give you the same equation. And let me just write down the equation over here, and that will just be 2. Obviously I can be a bit more explicit and show you. Okay, so let's do that instead of writing directly. So after this line, you can write it as this: -4, 2, 2, -8, 4, 4, x1, x2, x3, 0, 0, 0. So you can see that these 3 rows will give us only one equation. So let's write one of them. That will be, let's say, 4x1 plus 2x2 minus 2x3 equals to 0. Obviously you can divide this by 2 and you will end up with 2x1 plus x2 minus x3 equals to 0, right? Alright, so there is only one equation, and we are having 3 variables, so that means there are 2 free variables. So at this point we are just doing some linear algebra, and we have completely forgotten about the differential equation, because we only want to see what kind of eigenvector we can get from here. So I'm calling this x2 and x3 as my free variable. Obviously you can also go for x1, it doesn't matter, but for my convenience I'm taking these 2 guys as my free variables. So I'm gonna solve x1 in terms of these free variables. Yes, there will be minus, yeah, like this. That is x3 minus x1 by 2, right? And now I can construct the eigenvector v tilde. Since I have only one equation and this is the I can only extract out this amount of information. So instead of x1, I'm going to write x3 minus x1 divided by 2. I'm going to write x2. Sorry, this should be x2, not x1. And I'm going to write x3. Now what I can do is that I can multiply each of these elements by 2. You can you know this from linear algebra. This just means rescaling the whole vector, nothing else. So we can write it as x3 minus x2, 2x2, 2x3, like this. And since these 2 are free variables, this x3 and x2, and their choice is arbitrary, I can do right now the following. That is, I can keep out x2 over here. There will be a 2, and I'm gonna have a -1 over here, and there will be a 0 over here, and x3 on this side. So I'll have 1, 0, 2, and these two vectors like this, they are linearly independent of each other. And now since x2 and x3 are arbitrary, I can choose any value I want, and the most convenient choice is just choosing 1. So Obviously you can choose one and write it like this if you want. Alright, so this x2 and x3 doesn't matter, these are the main things. These are the things that we will need because they are kind of like the basis, and these choices are arbitrary. So let me get rid of this thing. Now we already had one of the eigenvectors. Okay, where was that? Yeah, this 1 1 2, and finally we have these two. And before we say that these are our 3 eigenvectors for this 3 cross 3 matrix, we need to check whether these 3 vectors, that is 1 1 2, minus 1 2 0, and 1 0 2, are they linearly independent? That's the question we ask. Because our solution of the differential equation should be linearly independent. This is the question we ask. And to find the answer, what we need to do is that we need to take these columns, we need to stack them up to form a matrix, and we need to calculate its determinant. If the determinant is not 0, that means they are linearly independent. If the determinant is 0, they are linearly dependent. So, as I said, stack them up. That means choose this, this, and this. You can choose in any order you want, because ultimately you are calculating the determinant, and it doesn't matter which which column comes first, which column comes second, it doesn't matter. So we need to evaluate the determinant of this thing, that is 1 1 2, minus 1 2 0, 1 0 2, and let's try to see what is the determinant. So this will be 1, there is a 4, and there is this 0, so this will be 4. There will be a minus and minus 1, and this will be 2. There will be a 0 over here, so this will be just 2, and finally you will have 1, there is a 0, and there is a minus 4, so minus 4. So you will have 4 minus 4 plus 2 equals to 2, which is not 0. So we can safely say, this v1 that we wrote, that is this guy v1, and we denoted v tilde that came in the combination of these two vectors, and let's call one of them as v2 and another one of them as v3. We can say that this v1, v2 and v3 are linearly independent. So our solution, that means our full solution, will be, this is our solution vector, let me give a bar, and this will be c1 v1 e to the power r1, where r1 will be the associated eigenvector, that means r equals to 0. So let me just write it over here so that you can understand what do I mean. v1 is the eigenvector that was associated with the eigenvalue r equals to 0. Okay, and the other twos are associated with r equals to 2. So r1t, c2 v2 e to the power r2t. Here r2 and r3 will be just 2, because 2 is repeated 2 times, right? And finally you will have our c3, and there will be a v3 e to the power r3t. And this c1, c2 and c3, these are arbitrary constants that are determined from the initial conditions or the boundary value conditions. So if you write this in its full glory, this will be just 1 1 2 e to the power 0, that means just 1, so let's not write it. And finally you will have c2, then v2 was minus 1 to 0, so minus 1 to 0 e to the power 2t, and finally you'll have C3 as 102 a to the power 2t, and obviously this x bar was containing this x1, x2 and x3, and now you can just multiply them and find out the individual solutions. So in this case we got lucky, but in the next video we're going to see a case where for a 2x2 matrix only one eigenvalue is possible and we won't have any idea what are the other eigenvalues, and those are called deficient matrices. So here though we got 2 eigenvalues, but at the end of the day we were able to extract out 3 linearly independent eigenvectors. But the case we're going to see in the next video, it won't be like this. So we have to introduce the idea of generalized eigenvalue. So this will be it for today, and I'll see you guys on the next lecture. Thank you.